Yes. Okay, that's fine.
Okay, Andrea, I think we can start.
Okay.
It's 5 past or 4 past. Yeah.
Yeah, okay. So, hello, everybody. I am Andrea Orlandini, a researcher from the National Research Council of Italy. And with Marcus Vince and Aurélie Clodic, we are the coordinators of the euROBIN topic group on AI and cognition in robotics. And today we are starting a series of seminars, and the first speaker is Michael Bitz. Michael Bitz is professor in computer science at the University of Bremen. I guess that everybody knows Michael for his very remarkable work in AI and robotics. He was investigating since a very long time the connections between symbolic AI and the robotics, and in particular the representation of knowledge and the execution of tasks. And in this area, he is also the head of the Institute of Artificial Intelligence in Bremen, and he is the coordinator of a German project called 𝐂𝐨𝐧𝐬𝐭𝐢𝐨 about the development of a knowledge representation framework for robotics. He was recently appointed with an ERC advanced grant about the investigation of the interaction between AI and robotics, and in particular to endow robotic platforms with the ability to understand the environment, understand the tasks that is supposed to execute, and to connect this AI part with the concrete parts, with the robotic part, so a more intelligent execution of tasks. And today, Michael will give a seminar about the insights of the euROBIN project, in which he is investigating actually, the project is investigating the connection between cognitive, cognition-based research with AI and with robotics. So, Michael, thanks a lot for accepting our invitation, and the floor is yours.
Thanks a lot for the introduction. Thanks a lot for being here. So, but first of all, I want to make a disclaimer. So everything I'm saying is my own personal view of the EU, in particular of the euROBIN project, what we might do there. And yeah, kind of Aline and all the other partners and colleagues might have in parts very different opinions about that. Yeah, let me start. So I think as a community, our vision is that we want to have autonomous robots that successfully act in the physical and social world, right? So we want to have robots that can assist people in kind of living more independently, that can support workers in a factory and cooperate with them in order to make their jobs easier. And I think if we are looking at robotics and in particular the computational problems involved in robotics, I think there's one computation task that I find kind of at the very core of our enterprise, and that is what I call solving the body motion query. So the general thing is robots will get underdetermined manipulation task requests, and they have to determine and execute a very specific body motion that achieves the desired effects and avoids unwanted side effects. And if you think about it, if you look at the brain and why nature has developed kind of or equipped humans with a brain, animals with a brain, I think it's mostly because of solving that problem, right? And even if we talk, it's actually a kind of controlling the muscles in the tongue in order to convince somebody else to do something, right? Which is also a successful action. So if you look at that, right, so the kinds of things we would like to do is we want to give our robots these underdetermined tasks like set and clean the table. And the robot should move its body in order to accomplish the task, right? And so in a way, the underdetermined task request set and clean the table should be sufficient as a piece of information that our robot control systems get in order to accomplish the task successfully, right? And it's very clear that kind of taking that very vague instruction, we have to kind of perform actions in a context-guided way, right? And the robot has to reason about the consequences of its actions in order to perform the task successfully, right? But if we are thinking about what does it mean that robots successfully act in the physical and in particular the social world, right? That's not enough. So robots in general have to act for the good of people, right? And that has particular consequences for the cognitive capabilities that these robots must have, right? And in particular, in terms of understanding. Kind of robots that are capable of acting for the good of people or are trustworthy, right, must understand what they are doing, why they are doing it, how they are doing it. They must be capable of answering what if question, right? What would happen if I use a different tool, if I perform that action with a different object? They have to understand the consequences of their actions, right? If a system cannot understand the consequence of the actions, how should it be possibly capable of acting trustworthy, right? And if we have the robots acting together with humans, the robots cannot simply learn a task in factory and then just kind of execute the learned task, but they have to do what others want them to do and how. Just how complex that is, just look at a particular example, right? If a robot is supposed to take advice by a human, right? So, and the human says something like, be careful, the water is hot. A robot has to make sense out of the advice, right? It has to kind of interpret the advice in its understanding of how the world works. It has to kind of reason about what changes in its behavior it requires, and then it has to implement the change in the behavior, which means reprogramming its own control system, right? And similar things is if the robot asks for help, right? So then it has to reason about its own gaps of knowledge, what the human might know that helps itself, and kind of how to incorporate the answer of the human in its own activities, right? So it's kind of a very complex kind of ensemble of capabilities that we are looking into here. So if we are looking at euROBIN, so euROBIN, and that's from the proposal, aims at pushing a particular kind of AI, which is called Cognition-Enabled, Transferable, Embodied AI. I kind of prefer the term AI core for AI-powered and cognition-enabled robotics, right? Which kind of argues that we are taking together the methods of the power of current AI methods, but kind of we combine them with the capabilities of cognition that we have studied in our European projects for such a long time. And we do that in the context of robotics, right? So what that means, cognition-enabled, transferable, embodied AI, we can see in this video, right? So it's similar to the video we have seen, but now you see kind of the robots performing the tasks in different environments. You see different robots performing the task, even different tasks. And you see what it means understanding what one is doing. That means you can simply ask questions to the robot, kind of give me a successful action of picking up an object, right? And the system kind of retrieves that action, kind of in this case a bowl. It has a complete representation of this activity. And if we are looking at the representation, we can click on every part of that representation and ask questions about that, right? So understanding what one is doing has very much to do with kind of being able to answer open questions about everything you're doing, right? And that's the way we should measure it. So again, disclaimer, so this is my own view. So if you're now looking at what the agenda of the European Commission is, right? So they want to kind of have AI with European values. So the vision here on the right side is to enable a responsible AI-powered green digital transformation for an attractive, sustainable, prosperous, secure, resilient, multicultural society based on European values with the highest living standard in the world, right? How the community is looking at us is that we as research communities, we kind of have the competence, we have kind of the knowledge to compete with the big players in the AI game. But they see that our big problem is that we are too fragmented to compete with them. And I share that view. So what they are looking is, they are looking into kind of the different communities that are concerned with AI, so AI or machine learning, data science, robotics. Kind of they want to bring these communities together by forming these network of excellence centers in the different areas, right? And these networks of excellence centers, they should kind of work together, build synergies, but also grow the community, right? And in order to do that, so it's important in that strategy that kind of those networks of excellence kind of build up and encourage other members of the community to contribute to what the European Commission calls the AI on-demand platform, right? Which is kind of a repository of assets that the communities provide for European companies and researchers to compete and kind of realize their research and innovation agenda, right? And we are in the robotics kind of part of that strategy. And in the robotics part, our network of excellence centers is euROBIN. And the part of the AI on-demand platform which should particularly target and serve the robotics community, is called EuROCORE. So if you're looking on how the euROBIN research network is actually implementing that, you see that essentially the agenda on the right-hand side. So the strategy is that the whole network should be built on EuROCORE, the European Robotics Collaborative Repository, which is intended for the community to share their programs, their data, and everything else we have in order to accelerate the progress of our fields. Around EuROCORE, we have 4 science areas. The areas which are more technical, which are learn and know. Interaction is the interaction, mainly the interaction of robots with the physical world. It includes robot hardware, mechatronics, but also the control for manipulation tasks. And very important is the human-centered part, which kind of pushes the aspect that all we are doing is for the good of people, right? And around those science areas, we have another layer, and this is a layer of cooperative competitions, right? The idea is that euROBIN organizes competitions in personal robotics, in robotic manufacturing, in outdoor robots. When the competitions are over, the code is shared, kind of the different research groups work together, push the research, and kind of leverage the insights from the last round of the competitions and push kind of the field together. Then we have the next round of competitions, and the competitions is a way to getting insight in the field. So now I want to talk a bit about the two technical pillars for cognition-enabled robotics, which are the science area learn and the science area know. So these two kind of science areas, they are not areas that compete with each other, or at least the way I see it. So I think it's more like in Kahneman's two-system approach of thinking fast and thinking slow. I think the machine learning methods, in the way they learn from huge amounts of data and compile that into end-to-end mappings from images to robot motions, built the system 1 of Kahneman's paradigm. It's kind of tailored for habitual behavior, so which means kind of the set of situations where we have lots of data about, and it's mainly context driven, so it's more a mapping, right? And it's, I think, kind of some estimate that system 1 behavior, our everyday activities that we don't think about, kind of amount to 95%, up to 95% of our activities, right? The know area is more the system 2 in Kahneman. So it's kind of, it's slower. It employs an ensemble of different cognitive capabilities like prospection, kind of access to memory and diagnostic reasoning, self-programming, and it's tailored for kind of solving novel problems in the world, going beyond the experience you have collected. And I think some of the distinct capabilities are prospective and deliberative reasoning, right? So the two areas are not competitors, but they are actually components that form a huge synergy, right? So system 2 is a driver that system 1 can actually learn to kind of deal with novel problems, but also to scale and kind of extend its capabilities to new things. So learning has kind of made spectacular successes in the last years, right? So and I think particularly interesting was robotic transformers of DeepMind, and some call it XGBT. The idea is we kind of develop large vision language action models. And you see here kind of from the Google paper, some of the example, right? Move apple to Denver Nuggets. Place orange in matching bowl, right? And you see, it's actually what we were talking about in the beginning in the initial problem, right? It's kind of, it's underdetermined task requests, and they are mapped to the body motion that hopefully achieves the task, right? But we also see that in that kind of mapping, that mapping is actually more a continuation of something you start. Kind of, this may be kind of the first part of a plan, and you just continue to expand it. So you're making kind of, you're solving action selection as a completion task, right? So how would I actually complete a task if I had read all the internet, all the Wikipedia entries, all the WikiHow entries in my life, and in a way the robot does what is the most reasonable continuation of accomplishing a different task, given it has seen all the text in the internet, all the images that are accessible in the web, and maybe kind of all the experience of robots can form in virtual reality environments, right? And kind of, this is a game plan that is done in that field, right? So you have the areas where deep learning had huge successes. So you have vision and kind of solving vision tasks on all images in the web. You have speech understanding and speech generation, which kind of has been pushed hugely. And we all know about ChatGPT and text, right? So that kind of gives us the way of having knowledge about instructions and action categories, right? Now, what robotic transformers are doing, they want to kind of combine that knowledge with experience knowledge from perception action loops, right? And the way kind of they see that this can go is that we have simulation engines in which we can run kind of programs or reinforcement learning processes. And in the virtual reality environments, we have rendering and simulation, and we can generate huge amounts of experience in perception action. And we kind of feed these learning cycle with huge distributions of data. And kind of their rationale is that this way we can push the general problem-solving competency of robots. So let's look at what they're doing. So that's kind of a very old example, but I think it's very telling about what these learning capabilities can do and what they cannot do. So it's an example from Ernest Davis and Gary Marcus. And so it says, like, you're having a small dinner party. You want to serve dinner in the living room. The dining room table is wider than the doorway. So to get it into the living room, you will have to, and then ChatGPT was answering, remove the door. You have a table saw, so you cut the door in half and remove the top half. So the thing is not whether that's actually right or wrong, but the thing to look at here is that this solution that ChatGPT is proposing is perfectly aligned with the computation task that ChatGPT is supposed to solve, right? The continuation of text, right? You see, yes, if you're looking at all the examples in the web, removing something that blocks might be just a good strategy, right? And you know that the thing blocking between the rooms are the door. So you also read somewhere that you can cut doors with table saws, and often kind of cutting things in half and removing the top might also be a reasonable strategy, right? So it's very well, can it be the case that it's the most reasonable continuation of the text we were prompting ChatGPT with, but it's not a description of a successful action, right? And we can tell that it's not it's not a description of a successful action, because if it was a successful action, it would have to achieve the desired effects and avoid unwanted side effects. And if one wants to do that, kind of the suggestions have to be tip the table on its side. If necessary, take the legs off the table if they are detachable. Remove the door only if it's really necessary. If you want to remove the door, you typically take off the hinges, but you better do not saw it, right? And sawing the upper half doesn't help at all, right? When you imagine it kind of from a physical point of view. And sawing a door that is fixed in the door frame with a table saw is also not a feasible action, right? So what kind of ChatGPT, ActGPT, or whatever is missing is that it cannot imagine the action it intends to do. And because it cannot imagine the action it intends to do, it can also not reason about it and form intuition about it, whether it's successful or not, right? So the second area, science area that we have in euROBIN is the area of no, and it's actually essentially targeting that. So if we are looking at the knowledge and reasoning enabled approach, which would be the system 2 of Kahneman's two systems approach, then kind of the game plan is that, right? So we have a context-specific body motion that achieves the desired effects, avoids unwanted one. And we have that underdetermined vague task request in the beginning. If we take that body motion and kind of subtract the information given in the task request, the rest has to be in the knowledge and reasoning of the robot, right? So that can not be another place where kind of the behavior, the successful behavior can come from, right? And kind of hypothesis that we can make is that the knowledge of a robot is composed of general plans, of knowledge and reasoning. So that's exactly kind of how it's done in the robot control programs that you have seen in the beginning, right? So if you're looking at the control program, so the control program looks in a nutshell something like that. So there's a plan, fetch and place, which takes an object and a destination. And at the location where the robot can see and fetch the object, the robot looks at how to fetch the object, and at the destination where it can reach and see the destination, it places the object. So this is kind of a very general plan that allows the programmer to do a lot of hand waving. So because it's so vague, we have to complement the generalized plan with a knowledge base. And the knowledge base is essentially a kind of a collection of general knowledge chunks. So something like cups used for table setting have to be clean and unused. Cups in the cupboards are usually clean. Cups and other containers should always be grasped from the outside, and so on. So the power of these knowledge chunks is that they are general, that they are universally quantified. So those knowledge chunks do not only apply to the objects that the robot knows of, but also to the ones that it learns later that they exist. So they are kind of very powerful tools to deal with the open world, the open environment, right? And they're not only kind of factual knowledge chunks, but there can be very general knowledge chunks, something like parameterize your motions to avoid unwanted side effects, right? So this kind of knowledge chunk requires the robot to have prospective capabilities to mentally simulate the kind of the changes of plans. And we can complement that with spilling is an unwanted side effect of pouring. And so it knows that it should actually look for a pouring motion that avoids spilling. We can also have other kinds of knowledge chunks, something like the pose to pick up a heavy pot, which can be learned from experience knowledge, right? So if you think about it, you have a robot and the robot is supposed to play Go. So you can have a general knowledge chunk, something like the best Go move in the current situation, right? And you can use AlphaGo to compute it, right? So that's kind of a perfect kind of knowledge chunk that your robot should use. There's one important category of knowledge which is extremely important for acting successfully in the world. And these are mental models of intended action. And that's known for a long time. So for instance, Craig, in the middle of the last century, he says, if the organism carries a small-scale model of the external reality and of its own possible action within its head, it is able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, utilize the knowledge of past events in dealing with the present and future, and in every way to react in a much fuller, safer, and more competent manner to the emergency which face it, right? So if you are looking at the example that we had was bringing the table next door, right? If our system would actually have a mental model of the intended action, it would be kind of, it would be much more competent in selecting the right way of carrying the table next door. So how do these, or how could these mental models of intended actions possibly look, right? So again, we are interested in mapping the inputs, which are essentially the underdetermined task requests, the images, prior knowledge into a robot body motion. But we are interested in a robot body motion that achieves the desired effects and avoids unwanted ones. And what are desired effects and unwanted side effects is determined by the task model or what we should do, right? So we want to explicitly represent the models of the objects that we are manipulating. We want to kind of represent the environment in which we are acting and the robot that we are controlling. We have seen in the videos that we can write generalized plans, and the parameterization of action description that these generalized plans, that they can generate the behavior, for instance, for successfully setting the table. And if we are reasoning before we are executing these body motions, whether the intended body motions achieve the desired effects, avoid unwanted ones, we can successfully act in the world. And that's kind of the game plan we are doing. So the big thing now is that, similar as in deep learning, where we have these huge networks, neural networks that we can now learn and execute, right? We also have for the mental models the technological base components that we need ready, and we can use them, right? So we know from the game engines that we can represent the world around us photorealistically in every detail that a robot needs to successfully act in the world as a virtual reality scene graph, right? And those scene graphs can be updated in real time so that we can act in real time in them. And all changes are computed kind of with us perceiving the environment as acting, operating in a natural way. We have very powerful simulators that we can leverage, and we have the technologies to write plans that work, right? So if we put these things together, right, so we can now have our table setting scenario, but now in a game engine environment where the robot acts, and that's exactly the program that we have seen the robot using in the real world and acting in that environment. And this kind of game environment is not only used by the robot to train it offline and get the capabilities, but it's actually building the belief state of the robot that is maintained by the robot in real time while it's executing, right? So this is kind of the machinery that allows us to actually have these kind of models running inside the robot control system. The other component we have always been talking about is actually the ability of the systems to understand what is happening in the world, right? And if we are looking at kind of scene graphs, we can have language grammars that actually interpret the simulations and translate it into models of intentional actions as they are used by cognitive psychologists, and represent them also in real time as representation. So you see here that we have a logical knowledge base that is completely building up the virtual reality scene. And because it's a logical knowledge base and the environment is a rendering, the robot can answer all questions about the environment, can also give the answers such that they can be grounded into the perception action system of the robot, so which gives the robot a very, very powerful mechanism to have belief states that facilitate successful action, right? Okay, so that's kind of the technologies we are pushing for. I have to skip those. So just one remark, right? So a difference between the machine learning approach, where you have an end-to-end black box system, right, is that you don't have, or you cannot insert the solutions we have already found in perception and robotics, right? So if you are looking into robotics, into motion control, right? So we have systems that we know can compute collision-free motions that are optimal with respect to almost arbitrary objective functions, right? And these are solutions that are provable correct. So if we want to have competent robot control system, I think it's stupid not to use and leverage these methods that we have and to insert them into our robot control system, right? Because at the end, they will help in every novel task, in every open context that we act successfully, right? And we kind of have so another task that you want to have in order to kind of get to competent robot control systems is you want your robot to watch the World Wide Web, to watch instruction videos, and so when the robot watches the instruction videos, it has to make kind of form descriptions of the actions it's seeing. It has to make kind of explanations about why the action that it sees in the video achieves the desired effects. And it has to have abstract representation, right? Because it doesn't know what the exact physical circumstances are, but it has to extract kind of the key motion patterns and transfer them into the own setting, right? So so for instance, kind of watching that, you see that the person is tracked. It's kind of incorporated into the mental model of the scene with the physics simulation, and then it can be transferred to another robotic system. So that's kind of the game plan that we are trying to do. Okay, so let's go to the last part. So if this is actually kind of what we are doing, and so one big thing about euROBIN should be EuroCore, the European Robotics Collaborative Repository, right? So that's actually probably the natural component where the research community can connect to the euROBIN network, right? So so if we want to kind of build such a collaborative repository successful, there's for me one big role model of how we can build such collaborative repository, right? And this role model is actually the development of the ROS community. So Willow Garage, which was, I think, kind of a company maybe with about 50 employees and key researchers in robotics. They have built the PR2 robots and a complete robot control system for manipulation on the PR2 robot. They have developed the simulators for that. They have developed the TF trees as a way of characterizing poses and motions of robots. 𝐂𝐨𝐬𝐴 as a simulator, 𝐂𝐈𝐍 as a visualization tool, and kind of they have given robots to key partners, but they also have given the complete software that runs on these robots to the community. So everybody in the world could actually download a PR2 in ROS and run a simulation of a tabletop manipulation task on its own computer, right? And they knew that this simulation that was kind of running on that simulation wasn't too far away from running their programs on the real robots, right? And that actually that kind of service enabled the creation of the biggest, most successful robotics community that we have today, right? So components of their success was they have provided a complete robot system, including the physical robot. They were not missionaries. They didn't tell other people how to write their programs, but they just provided generic enablers and laid open the application programmer's interface. And so the data structures and the APIs they are using, they became de facto standards, right? And they were absolutely okay with researchers establishing better subsystems. So for instance, move it instead of their own control systems. And this is actually what made the success possible, right? So, and if we want to transfer that, and this is again my very, very personal view, right? So if we want to replicate that success, we want to build something like a virtual research building, right? So we have here researchers worldwide that can sit on their computers, use Docker containers and download them. And using these Docker containers, they can actually enter the research laboratories in euROBIN, right? So for instance, a researcher can go into a lab, have the AMA robot of Tamim in Karlsruhe, but run that AMA robot into our kitchen and in our kitchen environment in Bremen, right? And in this way, they can do experiments and compare, for instance, a robot in Karlsruhe with the robots in Bremen and push that environment. So what we want to have is we want to enable everybody anywhere to actually participate in our research, right? Of course, subject to the European values. And if you are in that virtual research building, right, so you have Tamim and the AMA robot next door to Aline and the Justin robot, and you can just go next door and you are in another environment. You have our robots, you have the robots of any partner of IITs and anybody else there. So that's kind of the way how we envision, or how I envision that it could go, right? So if you are kind of entering EuROCore, so this is only in the building up phase, so not all is working, but I hope you can get an idea, right? So you're going into the research workbench for personal robotics, household robotics, and you see you have different environments in which you can perform experiments. You have our household environment, you have the RoboCup arena from Pedro in the RoboCup at home competition, our apartment lab. You have different robots like the PR2 Tiago robot and our Donbot, and you have different tasks that you can accomplish, right? And you click there, and hopefully, this. So the system comes up, and you have configured the environment that you have selected, right? So you can go there, you can run in a Docker environment, kind of the execution of the program, kind of the lab with the robot, and the tasks are set up and can be run remotely in the Docker environment. Hopefully it starts and doing the table setting task. And okay, now it's going. But you can also go and write your own top level plans for writing your programs, right? And here you see how that is going. Okay. So you also have a student interface. So you're going there, and the students actually participating in euROBIN, in euRobotics, they will have an open textbook where they can go kind of see the introduction of that. Let's see. Introduction. So you again have the PR2 robot and how a control system works. But most importantly, if you're looking at the textbook, you have actually the environments where the students can do research-oriented learning by going into our labs and actually doing experiments with our robots, right? You see here the textbook and how it's explaining what cognition-enabled robots are. You have videos in the textbook. David Vernon explaining cognitive architectures, right? And you kind of go then in the environment and you make exercises the way we have seen it before. That virtual building also provides a digital innovation and a platform for the companies in Europe, right? So here, actually, so for instance, kind of stakeholders in retail robotics, so kind of the owners of a retail chain can actually meet robotics manufacturers, right? And they can actually try out whether the robot built by a manufacturer work in the retail stores that these owners have. So we have here a model of the M retail stores, and that is actually built by robots of our startup company Ubica. So but that builds the idea that this virtual research building is also the door to getting innovation going into the field, right? And we also have competition arenas. So, for instance, the euROBIN competitions in personal robotics that involve things like opening boxes, kind of getting a delivery from kind of a delivery robot, and in order to receive the parcel, you have to open the door. So why do we want actually these?
Michael, an hour is nearly over. Can you come? Yeah.
I come to the end, yes. Yeah, so we want to build these complete research labs because actually they are the drivers for the community to build kind of common tools for building them up, because in the different research labs, you have a lot of redundancy in the software components, and you believe that others have better components, right? And we are pushing towards that, but let me finish up. So I think I wanted to get a couple of messages across. I think, first of all, there's a thing like cognition-enabled, transferable, embodied AI, which is the combination of data-intensive machine learning AI, robotics, and cognition. And in particular, in robotics and cognition, the European Commission is extremely strong, and we have our advantages. Cognition-enabled, transferable, embodied AI outperforms AI-powered robotics because they are kind of the system 2 component of complete control systems, and they enable robots to understand what they are doing. euROBIN can be the Ross and Willow garage of cognition-enabled, transferable, embodied AI, right? And the European Commission can help us in actually making a big impact here. The key, whether we can be successful or not, is actually whether we succeed in building a community around these ideas or not, right? And I think I would like to hope, I would hope that everybody is helping us to actually try to make that as a success. Thanks a lot.
Thank you very much. With this, so thanks a lot, Michael, for this really, really great talk. I would like to invite questions now. Since there are not so many, I guess you can just unmute your microphone and talk. If there's too many speakers, maybe raise the hand first. To get warmed up, Michael, I have my main concern always is how do you get the motions you have in simulation on the real robot in the real world, where everything is always a bit different to at least my experience, how it is in the simulation.
Yeah, so I think, I mean, the key is not so much the accuracy of the simulation, but much more important is that you don't know the physical parameters, right? If you see an object in front of you, you don't know how heavy it is, you don't know how slippery it is. So actually acting successfully in the environment where you don't know the exact physics parameter has to be dealt with by the control system. It has to be robust against these things, and it has to constantly monitor itself and look kind of what is happening if the mental simulation and the real world are not compatible, right? And it has to step in, kind of take the real world as assertions and go from there. So the key is building robot control systems that are robust against the difference between mental simulations and the real world.
Another question. Yes, go ahead.
Sorry, Damien Saleh from Technalia. Another question also is very nice, Michael, again. You showed examples of let's say, house lab, supermarket, thing like that. How difficult would it be to create a new environment more related to a manufacturing plant or a industrial workshop, you know, a site where these cognition-based robots could also evolve, but in a more industrial environment with the processes or internal logistics, thing like that. So how hard would it be in terms of simulation to create this environment, train the robot again, I don't know, create the skills and so on and so on? What would be the effort for that?
So we are basically building an infrastructure that is built on top of universal scene description format, which is a format that is, for instance, used in Omniverse by NVIDIA, Pixar. It seems to become a standard for many virtual reality applications. And we have kind of translators between USD and other formats into the universal scene description, right? So and that would imply that whatever you have as kind of one model in as a virtual scene graph, so NVIDIA has complete models of BMW plants, right? Can be semi-automatically transformed into the simulators we need here. And yeah, and so you have to kind of be careful about articulation models, modeling the inner operations of objects, and if you need that, you need to do additional work. But the idea is also that in EuROCore, we will collect such models and we will share them with the community. And so it pays off in an amortized sense, right?
Okay, for example, this 𝐂𝐸𝐳 that has this kind of environments. Would that be quite easy to convert, or do you see lots of work on that?
Well, I mean, if it's kind of a fully functionable with doors opening, closing on.
Yeah. Okay. Understood.
So yeah. So but
to go from the model to the logics, yeah.
Yeah. So, but it's feasible, and again, I think also those things can be automated at least partly.
Okay, thank you. More questions? Please feel free to ask. Michael is available only now. Michael, and Andrea, you have a question?
Actually, I was reading on the chat that one attendee asked about having the link to access the resources that you mentioned during your talk.
Yeah. So they are in the phase of building up. I sent you a link later. And yeah, so you can try out, and we are trying to push that, right? So we have an upcoming review for euROBIN, which I think is October 10th or so, and we are pushing kind of the functionality for that event. Yeah. Andrea, I sent you a link later.
Thanks. And actually, I have also a question. You mentioned the famous System 1, System 2 metaphor. And actually, I was thinking about different approaches in which actually there are more than two systems. So for instance, I was thinking about the T-Rex architecture in which there are actually a hierarchy of, they call them reactors. So a set of sense plan act cycle, or a set of reasoning modules that are interacting in different ways. So did you think that the simple separation between system 1 and system 2 is enough for, let's say, fostering your kind of reasoning, or a more complex interaction among more different modules, reasoning modules, intelligent modules, can be of help in this kind of work?
I think this is kind of an open research issue, right? So in this talk, I had system 1 and system 2, but system 2 is very complicated in terms of cognitive capabilities, right? So and there are different ways that you can make up kind of cognitive architectures, that you can decompose it in cognitive capabilities and representation that these cognitive capabilities work on. And I think this is open, right? And you can use your own model. But I think what is important is that we have a platform that can be shared and that everybody can work on, and that we can make the research work of the individual researchers reproducible by others, right? And that, I think, will advance the field substantially.
Thanks a lot.
Thank you. I can use this to announce that, yes, the video recording of this talk will be made available through euROBIN. It will take a few days, but it will be there. I mean, actually, for those who have been listening, it's maybe less interesting for those who sent the request. Are there any more questions to Michael? Michael, may I have one more?
Sure.
I loved your vision of ACT-GPT. You know, we are still using MoveIt, and yes, it's rather a pain than real fun. So when are we going to have ACT-GPT, you know, the first version, that we could actually then tune on our robot?
I think it's in a way it's there, right? So there are kind of rudimentary parts and control systems. I mean, in the Docker environments, you have complete control systems. You have these capabilities in rudimentary forms. We kind of have to push them farther, right? And but I think it's kind of developing perception frameworks where we can encapsulate perception capabilities in different ways, and the same is for motion control and everything else. Okay, so again, I think I believe that the problem is enormously complex. We only have a chance if we go with hybrid methods and trying to tackle that and learn from each other in order to advance quickly on it. It's probably kind of building a system that intelligently acts in a robot control system is one of the biggest science challenges that we have today.
Wonderful final word. Thanks a lot, Michael.
Thanks a lot for listening.
So audience, please do not leave. We have a few short announcements on, you know, how I-Core is progressing and actually where it's perfect for you to collaborate and actually help developing the roadmap in robotics for euROBIN. And with this, I hand over to Aurélie.
So yes, the first information that there will be an updated roadmap. So you remember that years ago, we've got this strategic research agenda. So huge work that has been done. So a new roadmap is will be written in the following months. So we have a first deadline, which is in November, the technical group meeting. So we will send an email with more information about that to you. So some information will be gathered by email, but also be ready because we will have to organize some interactive sessions with you to work on this roadmap. Another information is that following this seminar, we want to organize other seminars. The idea is mostly to talk about ongoing euROBIN project, so plans or research output, results, and so on. So please send an email if you have any ideas or people you want to have for this seminar or project. And the last information is that we will organize, so the technical group AI core, we will organize, so we will, as you said, Andrea, we send a proposal for a workshop at the next euROBIN Robotics Forum. So the proposal needs to be sent by the end of the month. So there will be one, we hope that it will be accepted, workshop at ERF on behalf of the technical group. I don't know if there is any question about those information.
Simply unmute the microphone and tell us. Maybe to add to this, I sent out, I think, an email already. At the 25th of October afternoon and 26th of October morning, there's going to be a TG summit. So all topic groups and all topic group members can participate. It's going to be online. Of course, more information will follow, but maybe reserve these dates, 25th afternoon and 26th of October morning. Okay, if there's no further questions, thanks, Michael, a lot. I really loved the talk. All the best for the euROBIN review. That's going to be always a big challenge, but it's a very big push because always a lot moves before these reviews. So I'm really looking forward to what's going to be there. And yes, please all contribute. I think this is our chance to become visible. Contribution is always that, you know, your work becomes visible. Thanks a lot, Michael. Thanks all for joining and have a nice day.
Thanks.
Bye-bye.
Bye-bye.
Thank you, everybody. Thanks a lot, Michael.
Bye.